Hello everyone, so I'm Michael Spence and I'm the lead researcher on CeADAR's Lighthouse project in semi and self-supervised learning, and in this video I'm going to give a brief introduction to self-supervised feature learning for image data. So I'll be talking about the motivations and the general background, and I will also talk about two specific examples of algorithms used to do this. So I'll start with just a brief recap of self-supervised learning. So self-supervised learning is the process of extracting information from unlabeled data using a kind of artificial supervised task called a pretext task. And then once this information has been extracted, it can be used for downstream tasks such as classification. So in the case of text, for example, even if your text isn't labeled, there's still important information contained within it. So the fact that the words woman and queen, for example, the fact that they often appear in proximity to each other tells you something about the text. And using some kind of supervised task like predicting missing words in sentences, for example, or predicting the last word in a sentence, these can be used to extract information from the unlabeled data. So in the same way that even unlabeled text contains important structural information, images also contain some information as well. So if you take an image and you reverse it, for example, it will still have the same semantic meaning in those cases. So if we take a picture of a dog and we reverse it, it's still a picture of a dog. It still contains the same kinds of information. And structures like this can be exploited by self-supervised methods to automatically learn features of images. So one example of these ideas being used in practice was a paper published by researchers at Berkeley in 2016, and they used automatic image colorization as a pretext task to learn features. So how they did this was they constructed a large neural network and trained it to take in one channel of a 3-channel image, which you can consider as just a black and white image, and train the model to predict the other 2 channels of the image. So yeah, you can see an example of this being done here, of the action of the model. If you feed in a black and white image of the Titanic in this case, then it automatically returns a colorized version of it. So even though this network is useful in its own right, it can actually be used for feature extraction. So how this is done is the researchers just considered the first few convolutional layers of the network and then added further layers on top of this for fine-tuning. So to test how well features were being extracted during the self-supervised pre-training, they tested on several benchmark tasks from the Pascal dataset. So there's 3 tasks here. There's image classification, object detection, and semantic segmentation. And while the network performed well on classification and object detection, it performed best on the semantic segmentation task. So this is the task of shading images automatically depending on where different objects are. So here's an example of an image being segmented based on the presence of a plane or not. So it was found by these researchers that their pre-trained network got very close to state-of-the-art performance in this semantic segmentation task. So the second example of self-supervised feature learning I have here is from a 2017 paper by Swiss researchers, and they investigated jigsaw puzzles as a pretext task. So what happened here is they would take an image, they would crop it randomly, split it into 9 different tiles, and then shuffle those tiles based on a predefined set of permutations. And then the goal of the model is to reassemble the tiles into the correct order. And the hope is that this task will allow the model to automatically learn important features of images. So this is what the architecture of their network looked like. So you would feed in all the different tiles. The final output of the model is a vector of about size 4000, because there's 4000 different permutations which can be applied to the tiles, and the goal is to just find which one has actually been applied to them. So yeah, they trained this network on millions of images, and then again, same as the previous paper from the Berkeley researchers, they tested their pre-trained network, they fine-tuned it on these 3 Pascal tasks, and funnily enough in this one, their model performed well on the segmentation and the classification tasks, but it actually performed best on the object detection tasks, getting very close to the state of the art for this particular benchmark. And object detection, yeah, is just the goal of putting bounding boxes around different objects in an image. So in the example here on the bottom right, there's a dog, there's a bike, and there's a car. Have all been detected in the image. So I've talked about 2 specific methods of self-supervised learning in detail, but it's important to note there's many other possible pretext tasks which can be used. So there's image upscaling, for example, turning low resolution images into high resolution ones, has been very successful. There's also many methods which incorporate generative adversarial networks into their pretext tasks. And there's also a paradigm called contrasted learning. One notable example of this is CeADAR, which has been very successful recently, and differs a little bit from the kind of normal pretext task paradigm. It's also important to note that many of these techniques can be applied to videos as well, so colorization, upscaling, things like that, yeah, you can just as easily use these methods for feature extraction on videos as well. So as usual, thanks very much for watching this video. If you have any questions about any of the topics covered in it, then feel free to reach out to me, or if you just want to get more involved in the Lighthouse project generally, then please send me an email. My address is just on the screen there. Yeah, so again, thanks very much for watching.